Hello, everybody. Welcome to the Neo4j Online Meetup. So in case you haven't joined us before, my name's Mark. I work in the Neo4j Developer Relations team in London. And so we do a few logistics, I guess, to start with. So if you haven't used YouTube streaming before, you can control the resolution that we're broadcasting at in the bottom right-hand side of your YouTube window. Ravi, who's joining us today, is going to be showing some code. And so when he's doing those sections, you'll want to set your resolution to at least 720p. If you have any questions, you can ask them in the chat on the right-hand side, or you can ask them in the Slack channel as well. So we're watching those, and then I'll ask them to Ravi. And with that, I guess we should introduce Ravi, who works for Autodesk, and he's going to be talking to us about finding connections between components, so DLLs, and all this type of thing. So hopefully it's applicable to you, even if you're not familiar with DLLs. So I guess Ravi, I'll hand over to you, and maybe you can start by introducing yourself. I guess explain your experience with Neo4j and how you got into it in the first place.
Mm-hmm. Absolutely. Thanks a lot, Mark. Thank you for inviting me for this talk. I work for Autodesk in San Francisco. So Autodesk is a company that produces, it's in the computer-aided design space. And you might have heard of the AutoCAD product, for example. So that's a product that our company produces. And so as you can imagine, so it's a company that's been around since '82. And it has a lot of kind of engineering-related software solutions for computer-aided design, both in the architectural space as well as the mechanical engineering, and now we have media and entertainment as well. So there's a lot of legacy code and a huge amount of it. And so I specifically work with the AutoCAD product line. And so that's the AutoCAD product, some of the verticals, and we also have a mobile and web app as well. And even there, we have literally hundreds of gigabytes of binary data in the product. And what I find over time is that there's a lot of inefficiencies in kind of dealing with this. And the solution that sort of popped up was when I saw a presentation of Neo4j and graph databases. It seemed a perfect fit for the kind of things we wanted to get out of the system and the efficiencies we were seeking. So this talk is about managing component complexities. I've been with Autodesk personally for over 20 years, worked on the AutoCAD product line, and seen technology evolve. And this is another, graph database is another step in that direction. So what I covered today is why did we solve what we solved? And then the what, how did we build our solution? And then I'll go through a demo and do deep dives into some of the implementation details. So as I kind of mentioned, producing complex products that are a combination of internal IP, third-party software, open source software, it's a lot of different things. And when you're talking about tens, if not hundreds of gigabytes of products, it gets pretty complex. So how do you kind of take apart the sausage and kind of detect the complexity, right? So for example, I've taken here an example of 3 of our kind of hero products. So on the left is something called Autodesk Inventor, which is a mechanical engineering product. And then AutoCAD, the AutoCAD family in the middle, and the right is used for building information management, a product called Revit. These boxes you see here are not just binary DLLs or components. They are actually collections of DLLs. They're sort of subsystems. And so this is just to give you a sense of the complexity we deal with, right? You have right from the graphical system to modeling engines to third-party source, to XML parsers, and so forth, right? There's a lot of different components involved. And what this diagram indicates is we have something called materials. So materials are kind of a definition of, for example, a surface type or how a surface would look like when you rendered it. And that's, as you can tell, common to a lot of different applications. And a change, let's say, to an API down there percolates to the system, right to some of the core apps. So if you look at the bottom, if the bottommost red box is the materials library and you make an API change, that change propagates through the system. And as you can see, naturally, right, the interdependency between these subsystems is a graph. So how do you kind of figure out, if I change this, what is impacted? Well, a graph seems like a natural approach for that, right? Here's another motivation of the why, right? So if you see, when people kind of work with systems, quite often it's maybe there's a wiki. Like this is a little example of a wiki where people have pooled together their own kind of internal kind of knowledge, right? And people communicate that knowledge and build, let's say, a diagram and maintain it manually. So if it's manual, it's potentially error prone, right? So somebody knows that a component A needs a certain other subsystem B, that dependencies actually needs to be monitored, right, by humans. There are other places that humans get into the system and you're managing, tens, if not hundreds of gigabytes of data. And that is, we have traditional tracking project management type of scenarios where, this component needs this from this previous release depended on this version of this component and so forth, right? It further gets, there's a lot of different places where, again, manual steps are involved. For example, if you're looking at, let's say, an update patch or a set of bug fixes, right? One of the things is trying to figure out, okay, if I want a minimal set of DLLs in this patch that I need to release, and these are the fixes that have gone in, what is the kind of closure? What's the transitive closure of the set of data that I need? Again, it's semi-manual. Can we automate that? So these are sort of the questions that came to my mind is, can we make some inroads into eliminating the manual process here, right? Now, I know that this is, I kind of gave a lot of context with existing large binary, traditional C++ type of applications. But a lot of what I'm going to talk about is very relevant to more kind of newer systems of packages and package management. And as you can tell, the complexities have just increased. So this is just a graph from modulecounts.com that shows just the sheer number of packages, right, in systems, whether it's Node package management, Node or NuGet and so forth, Maven. The key thing is that, in an organization, right, you may want to know what is the kind of landscape of dependency. So if I have this external third-party component, who among my products are dependent on it? So I may need to ask questions like that. And the system I'm about to kind of dive into in a little more detail, we'll talk about that a little bit as well, right? So like I said, it's not just about, though DLLs is that was the original motivation, I see the role of graph databases in managing complexity as bigger than just component dependency. So this is just a little example. If you take right in the middle, like components or artifacts, so components could be binary DLLs in the traditional sense. They could also be packages like node packages and so forth. I talked just about this piece where you're releasing a product and I need to get an efficient answer to a question saying, okay, I have this product that's, let's say, 100 gigabytes, and I see this old Microsoft DLL being used, right, of Visual Studio 2003. Who are the people using it and why? What is the chain of dependency? So that's the sort of question we originally started with. But as you can see, there are many other roles. So some of the terms may be very specific to internal to Autodesk, like Wingman is something, an internal code name for a project in terms of continuous updates and delivery. But you can see that knowing the structure and dependencies between components is important for other scenarios. And I'll bring up security, for example. Let's say we get a DLL that's flagged, and libxml2, right, or an OpenSSL vulnerability, and I need to know, and it's a specific targeted DLL version. I need to know what products are impacted. Again, a dependency graph could be useful. And then there are other scenarios, like even in ops, if I had a graph, then I talk about mashups in a moment. If the graph included services running in my cloud, right, and I had a link between the services and the binaries used for that services, I could figure out what services are impacted by something that's either a security flag or an update and so forth. So it's a bigger issue. So this is where I kind of hopefully I've given you some context to the problems that we're trying to address. And this is where the notion of graph comes into the picture, right? So if you think about the nature of data, we're talking about dependencies, and we're also talking about a fair bit of heterogeneity, right? So you could have a DLL, and so DLL to DLL dependency is great, but then in a company or in a product, you have DLLs are used by products. Products may belong to different orgs, right? So you have the notion of a graph where you have owners who own the product. You have products that use components and components that depend on each other, right? You could also augment that graph. So this is like an entity diagram, right? So you could, for example, have a node. So the red node is a security flag. So that I have an example later on. I'll run through which is a CVE, a common vulnerability and exposure. So you could link those sorts of that sort of information to your binaries. And so likewise, like I mentioned, a couple of minutes back, you could link services that are running on your backend to actually binaries consumed by that service. And so now you've increased the different types of information in your graph, and your graph gets that much more complex, but that much more rich as well, right? You can ask more interesting kinds of queries now. And so that is basically where the graph comes in, because you now have a set of data, no doubt a larger number of dependencies, but also a lot of heterogeneous types of dependencies. And so if you kind of step back and you take a look at what we're trying to do here, right? You have on one side a set of data, a diverse set of data sources. So you have artifacts, which are like, when I say legacy artifacts, I mean the traditional .dlls or shareable objects, .sos and .as and so forth. You also have newer artifacts with things like npm packages, NuGet packages, and so forth. You could also think of other forms of input data. So I have one example, and actually I may have some time, and I'll show you an example with the service declaration. So inter-service, so I have in the second column on the top, you see something called declarative inter-service dependency. So we have internal to our some of our services, we have health monitoring manifests for services that shows dependencies between services. Once again, the same graph can be used, or the same set of graph tools can be used to represent dependencies between services as well. So on one side, on the left, you have all these different sources of data. The problem we're trying to solve is how do we mash this data up so that on the right, we become more efficient at, for example, analyzing dependencies between components, answering questions. For example, if I flag something, who is affected, and so forth, right? And how do we implement this? So Occam, by the way, is just an internal code name I used after Occam's razor in terms of for this project I worked on. So this is how it kind of fits together, right? So on the left side, if you think about data on the left, you have diverse sources of data, and the system is architected as follows, right? So on the left side, you have different forms of processing of the input. So you have, so what I actually use, so this system was built pretty much in Python, right? There was a mashup that one of my colleagues did to the CVE database, and I believe he did .NET, which kind of shows you can actually process data from different sources. So the way the system is architected is you have a data source that mines data from different places. So for example, if you look at the leftmost column over here, I have a Python module that mines information from MSIs. There's a Microsoft format for installable packages. I wrote a Python module that mines information from DLLs and produces an intermediate JSON. And I'll talk a little bit about the intermediate JSON format that we produce. I also mined information from Artifactory. So for example, we have something, we use NuGet packages for some of our binaries. And in order to understand the consumption pattern of NuGet packages and who's dependent on what package and so forth, I wrote a script, again, Python and curl, combination of that, to using the Artifactory query language to query the repository and get information there. Likewise for NPM packages, so you can see that you have a set of diverse sets of sources of data, right? The HDS JSON this is the health data service check manifest I just talked about. So at the bottom, essentially every service that's running. So in the bottom left column, on the left on the leftmost column at the bottom, right, the HDS JSON represents a manifest that was parsed, and where the manifest represented inter-service dependencies. And all of these produce the same, a kind of a common JSON format, which is basically an edge list with properties and a notion of a primary key. And that common JSON is then uploaded or loaded into a graph database. And so there's just one utility that takes all of this different JSON and JSON from different sources and populates the graph database with it. So if you really think, really kind of how the system is built, right? You have a generic, very simple generic JSON graph representation. So you know it has information about version of the component, and then you can independently generate graph fragments. And it has the notion of primary key. So it's essentially a database neutral format. So it's a very simple JSON format. And then on the left, you have plugins. So these are the actual names of some of the Python modules and other modules. So you have a DLL to JSON that deals with legacy binaries. And then on the right-hand side, you have the actual JSON import, JSON to Neo4j importer. So that's how it's architected. And the right, we also built a lightweight kind of web query interface to it. So that's a highly scalable database on that side. And the thing with this architecture, since the import format is neutral, you can start adding different. In fact, we have created many different modules or plugins, I'd say, on the left side. So we have, for example, the CVE to JSON that takes the vulnerability information from the NIST. That's the National Institute of Standards vulnerability database. We have something that parses NuGet from Artifactory repo. From a node NPM, we have something from services as well. So essentially Artifactory packages and other sources. And it can be extended. So if you have other third-party tools like Palamida, Code Collaborator, and so forth, you can import data there from external products. And if you needed to put the JSON into other databases, you could as well for other purposes. So on the left side is where really the extensibility happens. And on the right side is completely reused implementation to import the data into the graph database. So for example, that's worked well internally for us. So if people wanted to participate and play with this application, I mean, play in the same or leverage the database that we built, they don't need to know Neo4j, right? So they just write a plugin that mines the data they're interested in and produces this generic JSON format. And then we use a common kind of database loader that takes the JSON and loads it into the database. So this is just an example. So we have all these different Git projects internally, and these implement essentially the left side, those yellow boxes that have different sources of data, that import these different sources of data. And so this is kind of an example of the graph format. So this is, again, it's a very simple format. I looked around, and there are other standard formats, but this worked best for me. It's just a standard edge list. The idea here is that you have a notion of a label, right? So these are the different categories of the node. So nodes have different categories. In this case, this just says test npm node. So this is, so if you walk through this example, this is a piece of JSON that represents two graphs. The first graph, right, has one node, right, and its properties, it says version 0.1.6, name says es-polyfill, say, right? So there's one node and it has no edges. So that's the first graph. The second graph in this graph list has 4 nodes and 3 edges. So you can see the nodes here, and so you have the node which says property. So the thing to note here, right, is that the way I represent nodes is it has labels and it has properties. The key thing is you'll notice that I have a field called match. So what match says is that I'm going to look for a node that has properties that exactly match these values when I try to merge this into the database. So every time I import a piece of JSON into the database, right, I'm looking to see if I can merge the nodes mentioned with an existing node in the database. And to do the merge, I look for properties that have I look for properties with the given names that have the same value. So this allows me to independently populate the graph database from different data sources, right? So for example, if let's say I produce the JSON for product 1, and then tomorrow produce a JSON for product 2, I need to make sure that product 1 and product 2 reference the exact same node in the database. And that's achieved through using this match field in the processor that loads the database. So it does a query looking for a node with these properties, and instead of doing a create or create a new node, it does a merge. And regarding the edge, so this is an ordered list, right? So it assumes, well, the node is an ordered list of nodes, right? And the edges is, again, it's an edge list representation. So it has a start index and end index, which says, so this says I have a node that goes from, an edge that goes from node 0 to node 1. And again, I can tag the edge, and I can add properties, a label to an edge, and I have properties on the edge as well, or type on the edge and properties on the edge as well. And so that's pretty much the graph representation, really. Again, I want to stress it's simple, but it's very flexible, because I can have any label I want for the nodes or edges, and I can mash up graphs to existing graphs by using the match property, the match list, meaning that if a node has a set of properties, I can specify which of those properties I use as a primary key. You can think of it as a primary key. So in this case, for example, let's go back to the node. So it has a test npm node. I have version. It has a version and name property, only 2 properties, and I say I want to use those as my matching criteria, right? So if I produce another graph with a node which has a property called version and a property called name that has exactly the same values, and I upload that JSON to the database, it'll point to the same node in the database. And so this is what the graph looks like. I ended up with 2 graphs and the edges between the nodes, as indicated before. And also, like I mentioned, the utility classes. So in order to make life easier for folks trying to import some of the data, instead of them having to deal with JSON and stuff, I just have some simple utility class that lets them just create a node as they would declare it, right? So node with labels and properties, and then I have a utility that serializes the data and outputs it. And so really, the JSON outputs to the existing graph, right? So it does. You can incrementally update the graph, right? And the extractors share a lot of code, so really they can focus on their business logic, right? Specifically on their business logic. Yeah, so like I said, there's a whole bunch. We've built a bunch of varied extractor types, and if we get some time, I can even walk through some of the code. It's a pretty simple, pretty at most a couple of 100 lines of Python or less to extract the data. These are the sorts of packages that we implemented. So the Win32 portable executable format, npm packages, NuGet packages, so forth. Yeah, this is an interesting one. There's actually, that's almost a separate talk, I guess. So one of my colleagues implemented ways to get at things like static libraries and statically linked libraries through leveraging an LLVM compiler. The other thing that we did is looking at log files to know which source files go into building which object module, right, or which DLL. And we did that using the actual build log file. Again, this was the MS build based output from the log file there. And then I mentioned CVE. This is an interesting one. This actually leveraged, so one of my colleagues implemented, once I did the basic DLL MSI dependency graph, he saw the potential of trying to use it to answer security kind of issues. So he wrote a little plugin that used some of the REST APIs that NIST provides. The National Institute of Standards and Technology has an open REST API to query their vulnerability database. And so he was able to query that database and then match it up to the existing graph database that we created. So these are some of the products. This is an example just to give you a sense of. So I mentioned AutoCAD. These are actually, so I kind of populated I've tried to automate the process of populating the database, and this is a list of products that we kind of run through in order to populate the database. So I'm going to, at this point, maybe do a little demo of what we have.
Quick question, Ravi.
Sure.
The JSON format you had, is that one that you created, or is that based on something you saw? Or
yeah, so it's sort of based on, this is I think it's loosely based on, I think, graph JSON, or there's other JSON formats, but I didn't quite get what I wanted out of it. So it's, you can say that it's maybe inspired a little bit more from my just traditional experience with graphs, which is just a node list and edge list.
Yeah, the only like sort of formats I've seen are, well, I've seen a graph ML. I don't know if you've seen that. That's like a XML.
Okay.
Quite similar sort of structure.
Right.
So did you, if I understood correctly, you had one JSON structure for each data set that you had. Is that right? Or did you have one across everything?
I have a common JSON representation.
Yeah.
But it's flexible, so you can specify the properties for nodes to be anything you like, right? So it just essentially it's a generic graph representation, and you can represent essentially represent subgraphs, and the way the subgraphs connect to the main graph is through the match property, right? So I can go back for again. Just it's a good point though. That's why I spent some time on this, because it's let's see. Yeah, I'll just walk through this again. So
Michael had a question. I'll read you it, and then maybe you can use an example to show how you do it. So can you use the match to connect relationships to nodes? For example, how would I connect a relationship to a node from another graph? Did you have a consistent identifier across different sources? E.g., how would you connect something in the security database to something from the DLL subgraph?
That's right. That's a great question. So the connections happen through nodes. So for example, in your security example, and I'll actually give you a demo of the actual use case. In the security example, you'll have a node for the vulnerability. So let's say you have a node with the CVE label, and then you have a node for the DLL. Now, when you process the product, data, right, you have a graph for the DLL that includes the DLL that has edges to other DLLs and so forth. When you process the vulnerability data, right, you get a node for the CVE, and you get a node for the DLL as well, because the CVE has information on the DLL name and version. And those are used as the properties that match that node to a node in the graph if it exists, right? So let's say the CVE processing came up with node, let's say libxml2 version 1.0, right? Yep. If there's a libxml2 version 1.0 in your existing database, then the import of the CVE data will merge that incoming DLL node, like XML2, to an existing node in the database. Is that clear?
Okay.
Yeah, and it uses the matching.
Yeah, I guess maybe it'd be easier to see. I think it makes sense, but I guess it's probably easier to see if we do the example, isn't it?
Absolutely. Yeah. And to a question about edge dependency. So the edge dependency really it's about nodes being merged, right? So if you want to have an edge from another node to if you want to actually have an edge from an incoming node to an existing node, then you need to know what that existing node's match properties are, and then the edge will kind of automatically point to it.
Cool.
Any other questions, or I can before I jump in?
No, there was an initial question about that was interested in how you got the data. So I guess you mentioned maybe if we get time we can have a look a bit at that.
Okay. I got different sources of data. You mean like from the DLLs?
Yeah, like how you got it from the how you scraped it, or I guess.
Okay. Yeah, we can walk through that. So there essentially there's ways to process the PE file format. So if you look at it's very different in different cases. So we can try to walk through some of the code.
Yeah, I'll probably do this. I'll do the demo first, and then if we get time, we can look at that again.
That sounds good. Okay, so I'm going to walk through a demo here to just show you the example, the utility of this tool. Okay, so let's so just to give you a sense of the database. So now I have this database here. It's populated with many different products and so forth. Oh boy, this is longer than. Okay, so different edge types, and it's about 733 megabytes. So it's not a huge database probably by your major graph standards, but it's pretty sizable, and it's compressed and all that, right, with what technology Neo4j uses. So it represented a few hundred gigabytes of data. And so what I ran, okay, let's go back to the query. So what I ran over here is a query that says, give me all DLLs with MSVCR in their name. And so what I'm trying to do here is I'm trying to see, okay, in my product, who's using old versions of Microsoft Visual Studio or the C runtime DLLs, and why are they using it, or what kind of products are using it. So when I run this query, I see, oh, I have all these different versions of these DLLs being used, right? And I want to zero in on, let's say, MSVRC 7.1. Okay, so if I zero in on that, and I say, okay, so who's using this version, which happens to be Visual Studio 2003. And then I actually say, oh, wow, okay, so these are the products. So if you notice the query, we went back too quick here. But if you notice the query, right, in my schema, right, I used labels, edge labels, to indicate the product. So DLL A is being referenced from DLL B through this product. So I have the product label on the edge. And so I try to, I return distinct types of products that are referencing this DLL, and I see these are the products that came up, right? And we have something called alias design, and CFD is computational fluid dynamics. So these are the products that were using this. So I'm kind of curious. Okay, so how did oops. Yeah, this is. So how did alias design use this? And so this is what it shows, right? So it's basically, I'm saying, give me the link. So this is how, let's see if we can go bigger here. Right, so this shows me the dependencies. And then there's something called FC check. And so I directly get who's using it. So I don't need to kind of walk around the halls and try to ask people, do you know who's using this, or spend time myself trying to figure it out. I have all this data automatically harvested, right? So I automatically know who's using this. Then I can figure out, talk to the product teams and so forth, and say, we're trying to move, or to the latest version and so forth. Can we make a project to kind of upgrade, right? So that's an example where we queried the database, and we figured out, mine some data for kind of code hygiene. So here's another example this is kind of ties to the security example. So if you look at what I'm trying to do over here, this, I believe, is the OpenSSL vulnerability question. And so if you look at this example over here, right? So these are the CVE nodes that were independently harvested. So there are a couple of things to note. So I didn't get into some of the detailed schema because I didn't think we have enough time for that. But so let's see here.
Yeah, I mean, you can probably explain it just enough so that the diagram makes sense. So I guess you've got.
Sure, absolutely. I'm going to do that in a second.
Cool.
So you see, here, this is a common vulnerability data, right? And it says this is the vulnerability number. If you look down at the bottom, it says the key is this particular vulnerability number, and it's referencing very specifically to a DLL, and this is the DLL that it's referencing to. And you can see that I have multiple labels on this DLL node. So this is a concrete DLL, and the piece about the schema I wanted to kind of talk to you folks a little bit about is the way we implemented our representation of dependencies is we have the notion of the actual concrete DLL, which is the name and version, and a generic version. Now, why do we have a generic version? The reason is that when you have a product that's dynamically loading a DLL, the one it picks up will depend on your runtime configuration, right? Example. And so when you have a product, let's say I have a product that references SSLEAY32, in absence of a manifest-based system that has a very specific version to load, the traditional DLL environment will load whatever's on the path, right, to the search path. So that's why we have two different versions. So you can see over here that there's a test development. So in this case, we thankfully, right, so this shows all the DLLs that are vulnerable. We really don't have let's see if I actually, yeah. So we really don't have a kind of exposure in the sense we kind of fixed. There's a test development. There's a OGS test development was a test app that was referencing this, but it's not actually shipping, right? So the edge that I just highlighted. But it did show in our case that, okay, if you look for vulnerability, OpenSSL, this is the kind of dependency that, that this is among all the hundreds of gigabytes of data, this is the DLL that showed up that has a reference through a product, and we can kind of dive into that and see, okay, what do we do about that, right? Let me show a little more. This is a bit noisy, so I'll try to get a simpler picture. Maybe this is hopefully.
Are you just wanting to show the schema, or do you want to show some specific part of the data set?
So I was kind of showing at this point. I was showing querying. I'm querying the database, right, for vulnerabilities around libxml2, right? Cool. So in terms of the
so that's in the middle, isn't it? In the light green.
Yeah. So this is the MSI JSON. So this is the generic node, right? The CVE is the so let me just separate out the relevant pieces here. Okay. So just let's look at 3 nodes here, right? And that'll give you a sense of the schema as well to some extent. And I have time, so I can walk through some. I'll just create a bunch of examples. So if you look over here, right? I knew there's an libxml2 vulnerability, and I'm trying to find. If you look at my query, right? I'm trying to find what are the DLLs that come from the product side that reference the same DLL reference from a vulnerability where the DLL is in libxml2. And so libxml2 is in this specific version of libxml2, 2.7.3.1, has known vulnerabilities, right? And I'm trying to find out who's referencing it. And so I can go through, so the NVD scan is the security scan. I can actually find there is something that, that shows up, that IO Core Engine, this version, actually is referencing this. So that's that's an example of figuring out, using the queries for using the database to query for vulnerabilities. You mentioned schema, so let me walk through. I have a few more canned examples, but I think maybe to your point, maybe it'd be worth illustrating a little bit about the schema, right? So okay, so let's start with the. Let's see. Let's see. Alias design. Okay, so yeah, use up. Okay, so if you look at here, let's try OrCAD. Okay, so this is a. So thinking about schema, starting with the product, I'm going to just show the product side of the schema and the different schemas. So this is a product, and a product has something called MSIs, right? So if you look at the edge, so again, this is the root. You can think of the root as the product node, right? And it has MSIs, which are essentially install packages, Microsoft install packages. And these contain binaries. Whoops, it gets busy really fast. So let me just. So these are a lot of different products over here. Let me just walk through this. All right. So if you look at ACDB, right? So essentially, I've got DLLs that this is a specific DLL that actually belongs inside of a product. So I can let's just do this. Okay. So in terms of schema, really, there's a couple of roots, right? You have products, and a component node is like a common root. So you have actually two roots for every product or product collection of DLLs. One of them is the product node. The other is a component node. So if you look at the component, essentially, it's a way of saying that all these DLLs belong to this specific product, right? And so you have different versions here of Inventor releases, right? So you can think of the purple nodes pointing to a specific release type. And then really the bulk of the graph database has to do with the DLLs. So in this case, so for example, you know that this concrete DLL, if you look down at the bottom of the screen, you'll see there's a hash key for the binary value and the name and version. So this is a concrete DLL. If you look at, let's say, take a concrete DLL and look at what it references, you'll get a whole bunch of things that it references. If you notice that one of the things it references are light green nodes, right? So and the light green nodes here are the generic nodes. If I can actually catch one of these guys.
Keeps running away from you.
I know. Yeah, I got too many nodes in here. Let me try something simpler.
But yeah, this it's a really nice example of how you can use the variable path searching. Because I guess that's what you were doing. You're like saying, "Show me everything."
Right.
More than one hop on a couple of the earlier ones.
Right. Mm-hmm.
So when did you show this to people, some of your colleagues as well? Did you use the Neo4j browser to do that, or did you build like an AutoCAD, Autodesk or AutoCAD type visualization as well?
Well, we have a lightweight one, but mostly we use just the browser.
Okay.
We have a lightweight web visualizer as well, but that has very specific kind of hard-coded queries. Now, this is the example. So I just made a simpler example. This is what I wanted to show you, right? So this is how dependencies. So I showed you the product as a root node, next component as a root node. Then you get to a DLL, right? You see notion here of a generic DLL pointing to a concrete DLL. So that's a key part in the schema, which means that a generic DLL, now if I open this, it's going to get pretty busy really quickly. But the point I'm trying to make is you may have two concrete versions of a DLL, right? So this has a concrete version information in here. Let me make this big. Right? So you can see that this has a concrete version. This has a concrete version. This is the generic version. So what this means is that when you're talking about DLL references, right, you can get a reference when you have a DLL referencing another DLL, what it resolves to at runtime depends on the path, like I mentioned. And so you may have many different DLLs referencing ACDB20, but which one it picks up will depend on the path. Now, if I expand this, you'll see that there's a lot of people who reference it. Well, it isn't too bad. So you can see a lot of people are referencing this generic DLL, right? So this generic, so for example, these are all the DLLs that reference ACDB20. And if you want to know specifically where which product these come from, you can look at the edge. So hopefully this gives you some sense of the DLL schema. Like I said, there's no single schema because there's many different types of data in here, right? The key thing is if you go back to my PowerPoint where the graph is very heterogeneous, right? It lets you mash things up based on property name. So what I've shown you here is just the traditional DLL schema. I'll show you something more manageable. So this is the service schema. Now, this has nothing to do with DLLs. I'm using the same graph mechanism or same import mechanism. And these are some of the services that we have. And using like the service manifest JSON, you can represent which services depend on which other services. So in this case, you know that we have identity and access control management and so forth. And you have the inter-service dependencies. So this is a completely different form of representation of data, right? Okay, so let's try something. Let's get back to the actual scripted demo. So yeah, this is another example. Yeah, this is a query on the same database. I want to know who's referencing a specific service. I have something called WithDM, and I want to know which of my services are referencing this. This is a completely different. I mean, it's a completely different use of the same graph mechanism. I have another service maybe called OSS. I need to know who's using OSS. So that's another example over here. So I'll stop here. Maybe I can go through a few more queries, but I'd like to make sure I clarify some of the questions. I think most of the questions seem to be around what is the schema and so forth. Hopefully that's a little clearer.
Yeah, what happens if you do call db.schema? Do you have that procedure available? Hopefully you do. You do call space db.schema. Yeah. What does that do? Something.
It's something, I don't know.
So that tries to draw a graph of the graph, although I don't know what it's doing now.
Yeah, it seems to be thinking or stuck or something. No? I'll come back.
It's strange. Yeah, no, it really comes back straight away. I don't know what's happened that time.
Uh-oh.
then I guess the other thing people were asking about was, for example, do you
Oh,
have
there you go.
your? Oh, there you go. Wow,
Okay.
there's a complicated one.
That's why
Oh, it's because you've got. Oh, yeah. Actually, that leads us to another question. Actually, was your relationship types all are really, really specific, aren't they? They've got like
yeah.
very specific names, and I think that's why the DB schema
Okay.
diagram has taken a long time to draw. Because is there any reason on for making them so specific as opposed to just building like a more generic relationship type and storing the specifics as a property name?
Yeah, so one of the things that when we early on looked, right, is if a lot of our searches are to make our searches efficient, right, we have
Yeah.
very targeted searches. So if we have to do a property search based on an index and so forth,
Yeah.
that'll be more expensive because edges are super efficient. Like navigating a relationship is super fast. And
So
so actually,
so does the person querying always knows like what's those, so like CFD underscore and then the number that would be like
yeah.
the domain knowledge of the person. Oh, okay.
Yeah, so typically, so the good question. So typically, we're either interested in all the relationships to a node
Yeah.
or a very specific one.
Oh,
Because
so
a
that's why you
relationship,
can do your like star search.
right?
Okay.
Yeah, exactly. So we're interested either in all the products using something or, okay, for this product, what's using this? So that was fastest, fastest implemented using just your edge lookups in Neo4j are
Yeah.
really fast, I guess. So.
Cool. So yeah, I took you away from something. I can't remember what you
No,
were
no,
going to
it's
say.
fine. I would, yeah, main thing is to get this across. I mean, people wanted to know about, so again, this is a little bit unscripted, which is fine. But I mean, just, oh boy, this is, okay, I'll just get another local host. Yeah.
Your browsers are not too happy with us anymore.
Yeah, it's fine. I still have my Hangout, so. Yeah, so I can, yeah. So some of you folks were interested in just how some of this thing, how some of the parsing works, right?
Yeah, that's right.
So if you look at, so I can walk through some of the code, it's fine. So, so I use something called the P file library. So if you look at, this is just the DLL parsing piece, right? So if you look at the P file,
Are you able to zoom it in a little bit?
okay.
Maybe Command plus or. Yeah, that's a bit better.
Okay.
So are these scripts on GitHub somewhere, or are
they're internal, but so that's a good question. I'd like to at some point, make it available.
Cool.
But yeah, there's nothing proprietary here.
Okay.
Yeah. So essentially this. So if you look at, so let me go to the top. So really, you have, the key thing I use here is the PE file, which is a Win32 portable executable file, kind of that takes it apart, and that's how we crawl. I mean, we figure out dependencies automatically. And if you look at what the code is doing, right, it's essentially crawling the directory. So you point it at a directory, it crawls. So these are the extension types it looks for, right? Then it uses the PE file to extract kind of information from the go here. So there's the PE file, this whole module, Python module that gives you a lot of information from the portable executable file, and you build your node from that. That's pretty much it, right? So, and it includes getting dynamically loaded DLL dependencies. So, so for example, the portable executable file has the notion of a directory import entry, right? And so it walks that import table and gets information from there. And so that's an example of how I think one of the audience members asked about that. So that's basically how the DLLs are processed. And this is just a 140, 150 line Python file that spits out the DLL. Spits out the DLL information. some of the other things, let's see if I have them here. Oh, let's see. Yeah, this is a completely different. Oops, no, this one doesn't have it here. Okay, parse. So this. So node packages are done very differently. So for example, node packages will actually execute a curl query, gets the output there, and then process the manifest. But at the end of the day, it produces the same nodes and edges and populates the JSON. So this has, so that's the whole point, right? So you can get data through very diverse sources. Yeah, so. So that's pretty much it. Any other questions I can answer? I can do some more examples.
No, there are none at the moment. I guess we're getting pretty close to the hour. So I guess just to say to everybody watching, if you liked the talk, don't forget to like the video. And if you've got any questions, I guess you got 4 minutes until we hit the hour. So
so
ask away.
So there's one other thing I can potentially show is NuGet. So this is an example of a NuGet component. So as you can see, these are very different sources of data. So this was got from a NuGet scan, and if you look at it, shows. So the interesting thing is that it's So this is an example of you have NuGet components that also are hooked into the same database. So the names over here on edges are the actual NuGet components. So these are essentially zip files in Artifactory that has been mashed up with other DLLs in the database as well.
So we've got another question, which is, do you hook this dependency graph up with like services that are running, and then to processes, and then back down to the applications that are running on there?
Oh, so this is a static database. So one could envision it being used for that scenario. If you the HDS service example, this one that I showed you, is based on the inter-service dependencies through a static manifest on the service. But that'd be an interesting use case, right? Where you can actually maybe mine log files or something and create dependencies and then connect that to actual binaries.
Yeah, that would be a fun one. You're like, oh, which machines have this DLL that I need to? So I need to like get rid of those machines, I guess.
Exactly.
Apparently, I've misunderstood the question. So the question is the service information fully connected down to the DLLs they use? Maybe that may.
Oh, in my example, no. In my example, I have just the services using the same generic graph JSON format. I had a case where I manually connected it, so I wrote some actual Cypher code to connect it to a DLL because I was kind of interested in understanding the cascading service dependency. But that is something that could be done. It just we haven't done the work to do it yet.
Cool. I guess we can probably wrap up.
Okay.
Wrap up then. I think you've answered all the questions that people had. So thanks everyone for joining, and thanks to Ravi for coming along to present. And if you want to share the video, it's going to be the same link as what it is now.
Okay, cool. Great. Thanks a lot. Thanks for having me.
Thank you.
All right.